Hi grade 12s and welcome to this video. In this video, we are going to be working on KZN's grade 12 mathematics common test, and this is for April 2021. So the test is out of 100 marks and it is a 2-hour paper. I also want to mention that I downloaded this paper from Essay Exam Papers. Here is their link. You can use this as a resource website so that you can practice on past question papers. Okay, so then we have the instructions. Make sure to round off to 2 decimal places, and let's move on straight to question 1. Okay, so question 1, given the quadratic sequence 44, 52, 64, and 80, so we've been given 4 terms, the first question is to write down the next 2 terms of the sequence. So remember, it's a quadratic sequence. In a quadratic sequence, we have a first difference and we have a second constant difference. So since we need to find term 5 and term 6, this is how we're going to find it. Let's go ahead and first find the first difference. So we'll find that by saying 80 minus 64, which is going to give us 16. And then 64 minus 52, which is 12. And then 52 minus 44, so that's like 6, and then so that's 8. Okay, so now that we have our first difference, that's our first difference, we have to find the second difference. So we'll find that by saying 16 minus 12, which is 4, and 12 minus 8, which is 4. So you see that the second difference is constant. Now this is how we're going to find those next 2 terms. Because we know the second difference is constant, if it's 4 here, it's going to be 4 again. Now we can find the next term in this first difference. So by saying 16 and plus 4, because this is a positive 4. 16 plus 4 gives us 20. Then to find that fifth term, we're going to take this next term and add it to this first difference. So that is 80 plus 20, which is 100. Okay, so there we found the fifth term. Now we still need to find the sixth term. We will do the exact same thing. Our constant difference is 4. So 20 plus 4 is 24. 100 plus 24 is 124. So it means that the next 2 terms are therefore 100 and 124. Okay, so that's for 2 marks. Moving on to the next question. Okay, so 1.2 says, determine the nth term of the quadratic sequence. So the nth term of the quadratic sequence is speaking about the general formula of the quadratic sequence, which looks like this. Tn is equal to an squared plus bn plus c. So you see that in order for this to be complete, we need to have the value of a, b, and c. Okay, so this is how we're going to find those. We're going to use this pattern that we have here. So let me just take this and paste it down. Next, we're going to look at all these terms here, the first terms in each row. You can circle them because we're going to use these numbers. Then the second difference, we're going to make the second difference equal to 2a. So 2a is equal to 4. Then the first term in the first difference, we're going to make that equal to 3a plus b. And then the first term in the quadratic pattern, we make that equal to a plus b plus c. Okay, so that's what we're going to do there to find a, b, and c. Then to find a, you start with a. We're going to start down here. The equation we have is that 2a is equal to 4. Then to solve for a, we divide both sides by 2. And so therefore a is equal to 2. Okay, so we got a. Now the next one, to find b, we say 3a, but we know what a is. A is 2. So 3 times 2 plus b is equal to 8. And then 3 times 2 is 6, but I'll hold on to that. And I know I have b here, so b is equal to, and I'm rewriting 8 down. I know 3 times 2 is a positive 6. If we take that positive 6 over, we get a negative 6. So b is equal to 2. Okay, and then a plus b plus c. But I know what a is, it's 2. I know what b is, it's also a 2, so plus 2. And then plus c is equal to 44. Okay, so let me start with the c because I know I can add those two. So I'm dropping down c is equal to, I still have a 44 here. 2 plus 2 is 4. If you take that positive 4 over, it becomes a negative 4. So c is equal to 44 minus 4, which is 40. Now you see we have a, b, and c, and we can substitute it into this equation, this formula. So Tn is finally equal to Our a is 2, so 2n squared. Our b is a 2 plus 2n, and our c is a positive 40 plus 40. And there we go. That is the n term of our sequence. Okay, moving on to the next question. Question 1.3 says, calculate the 30th term of the sequence. In other words, they're asking you for term 30. Okay, and just exactly as I have term 30 here, I'm going to use the Tn formula to find this term. Now, do you see that I said T30? In place of n, I replaced n with 30. So that's what I'm going to do in the formula. So T30 is equal to 2. And then in place of n, I'm going to substitute 30 all squared plus 2 and replace with 30 plus 40. So you can put this onto the calculator and find out what term 30 is. And when I substitute, I get 1,900. That is term 30. Okay, so that is question 1.3. Moving on to the next question. Then question 1.4 says, prove that the quadratic sequence will always have even terms. Okay, first of all, that quadratic sequence, right, for it to have even terms, we have to think about what controls the terms in this pattern. What controls the value of the terms in this pattern? It would be the Tn formula, because when you substitute a value for n, it gives you a term value. Those are the terms that you're getting. So this controls the terms. So we're going to need that formula first of all. Okay, so what are we doing with this formula? We need to prove that this formula, when you substitute your n values, which is of course going to be natural numbers, because you're substituting numbers like 1, 2, 3, 4, numbers that are just counting numbers, right? You need to prove that when you substitute those, it's always going to be even. So in order for us to be able to prove that, we need to understand what exactly makes a number even. Okay, so a number is even when it is divisible by 2. When you can divide a number by 2 and it gives you a whole number, then you know that this number is even. Okay, so really all we need to show them is that this number actually can be divided by 2. But we're not going to do this by dividing this by 2. We're going to do this by showing them that we actually have a factor of 2 in this expression. It's kind of like this. To prove that the number 10 is even, I can rewrite it to show that it has a factor of 2 in it. So I can take out a common factor of 2 out of 10. And if you divide 10 by 2, you get 5. So I can show them that this is even because I can rewrite the same number as 2 times 5. Okay, so that's kind of the idea of what we're doing here. To show it's even, we need to show that there is actually a factor of 2 in here. So look at this. Look at the first, second, and third term. Do you notice that they all have a factor of 2? The highest common factor is 2. So that's what we're going to do. I'll take out 2 as a common factor, open the bracket, and then what is left? Just say 2n squared divided by 2. You're left with n squared. And then positive 2n divided by 2, you're left with positive n. And then positive 40 divided by 2, you're left with positive 20. And like this, I'm showing that there is a factor of 2 in this expression. So definitely it is even. And any number that you put in n, of course, given that it is a natural number, it's always going to end up being even. So I'm saying that this is always going to be even as long as you don't have n being fractions and stuff, but terms are not really fractions. So we can just clarify that, because in this case I'll think no, it's okay because they know that terms are not fractions, but you can just add on to that by saying as long as, or you could say for, where n is an element of integers. As long as n is an integer value, then it's always going to be even. Okay, question 2 says the 8th term of an arithmetic sequence is 31. Let's already put that down. So the 8th term, meaning term 8, okay, of an arithmetic sequence is 31. And then they tell us and the sum of the first 30 terms is 1,830. So the sum of the first 30 terms, that is the sum of 30 terms. It's equal to 1,830. Okay, the question is for us to determine the first 3 terms of the sequence. So let's think about that. How do you find the first 3 terms of the sequence? Well, if you had the formula of the pattern of the sequence, you can find that. Okay. So in order to find the formula, you really just need your first term and your constant difference, because an arithmetic pattern's Tn formula is this: a plus n minus 1 times d. Okay, so let's go ahead and use what we have. So since this is term 8 is equal to 31, we need the Tn formula, because that's the formula that speaks about terms. So Tn is equal to a plus n minus 1 multiplied by d. And we're going to take this information and substitute it into here. So T of what? T8 is equal to a, we don't know what a is, plus n, we know what n is. You see that we substituted in place of n8. So we're saying 8 minus 1, and then we have a difference, which we also don't know, so we will leave it open, times d. And then this means T8, right? We know the value of T8. The value of T8 is 31. So in place of that, we say 31. Therefore, 31 is equal to, we still have our A, plus 8 minus 1 is 7. And you see that D has been multiplied to that. So 7 times D is positive 7D. This is the equation that we have so long. Okay, so let's hold on to that equation and let's find out what this equation is going to look like. So this one says the sum of 30 terms. So we need to use the sum formula of an arithmetic pattern. Remember that there are two formulas. But because we don't know what the last term is, we know this is the sum of 30 terms, all right? This said the 8th term, not the 30th term. So we don't know what the last term is, so we are going to use the other formula instead. So that is Sn is equal to n over 2, open bracket, 2a plus n minus 1 multiplied by d. Okay, so let's go ahead and substitute. So we're saying S of 30 terms is equal to n is 30 over 2 multiplied by 2 times a, we don't know what a is, plus n is 30 minus 1 times d. Okay, we also don't know what d is. Then we know what S30 is. So we're going to replace that. In place of S of 30, we say 1830 is therefore equal to, what is 30 divided by 2? That's 15. And then this we can just simplify. So this is being multiplied by 2a, and then we have 30 minus 1, which is 29. And d is multiplying by that 29. So plus positive 29d. Okay, so let's just distribute where we can. So long we have 1830 is equal to, and let's multiply in. So 15 times 2a is 30a, and then 15 times 29, let's see what that is. So you see that is 435. So we're going to say plus 435d, and this is what we have so long. Okay, so do you see that we have two equations? But what I'm going to do here is this formula, I'm going to make something the subject. I can see that a is nicely on its own with no coefficient other than 1 there. So I'll make a the subject. I'm saying a, let me actually leave that in red. A is equal to, and then I still have 31 on the left. So I leave 31, and what's coming over is the 7d. It becomes a negative 7d. Okay, and now I'm going to go ahead and call this my equation 1, and I'll call this my equation 2. So in order to solve for something, I'm going to go ahead and, because this is on its own, I'm going to substitute equation 1 into equation 2. And when I do that, so it means that whenever I see an a in equation 2, I just replace it with 31 minus 7d. So I have 1830 is equal to, then I see 30 and I see a. So in place of a, I replace it with 31 minus 7d. And then continuing, I have plus 435d. Okay, so now we just have to distribute and simplify. So this is 1830 is equal to 30 multiplied by 31. Let's see what that is. And we get 930. So 930, 930, and then 30 multiplied by 7. So let's see that. Okay, so it's actually negative 7. So that's a negative 210. So 30 times 7, negative 210d. Okay, and then we just continue here. That's plus 435d. Okay, so add your like terms together. You see everything with d, just add together. And Here we can just go ahead and say 1830, and we're going to take the 390 over, so it becomes minus 930, is equal to, what is negative 210 plus this? Let's see what that gives us. And that gives us 225. So 225 is what we get, 225D, okay, because it was in terms of D. 1830 minus 930. So 30 and 30 can cancel. 1800 minus 900 would be 900. So 900 is equal to 225D. Okay, then in order to solve for D, we're going to divide both sides by 225. So divide by 225. So we just need to find out what 900 divided by 225 is. And you see that that gives us 4. So that is equal to 4. Okay, so now that I got D is equal to 4, what I can do here is call this equation number 3, since I have 1 and 2. So this is equation number 3. Now, in order to solve for A, I need to substitute equation 3 into the equation where A is nicely the subject. So substitute equation 3 into equation 1. Okay, so equation 1 says A is equal to, so A is equal to, and we have 31 minus 7, and in place of D, we're just going to substitute 4. So this is equal to, you can just go ahead and substitute it into the calculator, or you can calculate it manually. That's also fine. 31 minus 28 is 3. So there's our answer. We just have 4 and 3, right, as A and D. Now, in order to find the first 3 terms, because that's what they asked for, the first 3 terms, let's think about that. You can go ahead and find the formula if you want, but it's not that necessary. Look at why. This is an arithmetic pattern, okay? So think about it. The arithmetic pattern, A stands for the first term. So you know the first term is 3. D is the difference, meaning what do I keep adding to get to my next term? So if I wanted the second term and I know the difference is 4, I just have to say 3 plus 4. Then I'm going to get the second term, okay? So whatever that is, you really add it. 3 plus 4, that's going to give me 7. So that's the second term. Then to get the third term, I do the same thing. I know that the difference is 4. So 7 plus 4, that gives me 11 as my third term. So therefore, my answer is the first 3 terms is 3, 7, and 11. Okay, so that is question 2. Moving on to the next question. Then we're on question 3. 3.1 says the second term of a geometric sequence. Second term of geometric sequence is 5 over 128. And then the ninth term is 5. And we need to determine the value of the common ratio. Okay, so let's write down what they gave us. They told us the second term, so that is term 2. That is 5 over 128. And they told us that the ninth term, which is term 9, is 5. Okay, again, this is just a simultaneous equation. So because we're speaking about terms, we're going to be using the Tn formula of a geometric sequence, which is Tn, and they're both Tn really. So Tn is equal to A multiplied by R raised to the power of n minus 1. So here we're substituting term 2. So saying term 2 is equal to A, which we don't know, multiplied by R, we also don't know that, to the power of n, right? But which is 2. We know what n is, minus 1. And then what is the value of term 2? It's 5 over 128. So we'll say 5 over 128 is equal to, and we have A multiplied by R raised to the power of 2 minus 1, which is 1. And so you don't have to really write that 1. It's just A times R that we have there, or AR. For the other one, we're just going to say T9 is equal to A, again, multiplied by R raised to the power of 9 minus 1. And then term 9 is equal to 5. So 5 is equal to A multiplied by R raised to the power of 8. Okay, so this is the 2 equations we have. So in the previous one, in this question, question 2, that's really where I just decided to make something the subject and then substitute. That's what I wanted to do here, but it feels easier to just work with dividing. So the reason we divide is because it's geometric, okay? You wouldn't divide in an arithmetic sequence, for example. So this is going to be equation 2, and then that is equation 1. So I'm just going to say equation 2 divided by equation 1. So I'm taking the left-hand side divided by the left-hand side. That is 5 divided by 5 over 128, which is equal to the right-hand side divided by the right, which is a times r raised to the power of 8, divided by a times r. On this side, we're dividing. Remember, this is a number, this is a fraction, a whole number. You have to divide fraction by fraction. So to make this a fraction, you can just put it over 1. So because we're dividing, we will tip and times, which is 5 over 1. And we change this to a multiplication sign. So that is the times part. The tip part is where you swap numerator and the denominator. So that's 128 over 5. And this is equal to, you see here that a is going to cancel and you're left with the r. So r to the power of 8 divided by r is r to the power of 7, okay? Because you subtract the exponents when dividing. So here we're going to have the 5 over 1 multiplied by this fraction. Say numerator times numerator and denominator times denominator. But I can clearly see here that diagonally 5 can cancel. You can cancel out common factors diagonally when multiplying fractions. So I cancel the 5 here and cancel the 5 here. So I'm left with just 128 over 1, which is 128, is equal to r raised to the power of 7. Okay, so do you see here we have 128 is equal to r to the power of 7. We need to solve for r. And what's stopping us from solving for the r? The 7. So we need to get rid of that exponent of 7. How do we do that? By finding the 7th root of both sides. It's like square rooting both sides, but it's the 7 this time. So I'm going to say the 7th root here and the 7th root here. Okay, this is not an even number. If it was something like 2, you need to remember to say plus minus in front of the number. But this is an odd number, so it's fine. You don't have to write that. Remember that for even numbers. So the 7th root of 128, let's find that. And you see the 7th root of 128 is 2. So it means that r is finally equal to, when we find the 7th root here, they would both cancel. R is equal to 2. And that's our common ratio. So there we go. That's how we found that. And that is for 5 marks. Moving on to the next question. Okay, question 3.2 says, calculate the value of m if. So we've been given the sum, this is sigma notation, the sum starting from k is equal to 1 all the way to m of, and we have a pattern with the formula -8 times 0.5, which also remember that is a half. 0.5 is a half. And they tell us what the sum is equal to. Okay, now notice that this is for 4 marks. When it's for 4 marks, the actual calculation usually takes 3 marks because they need to give you a mark for substitution, for either using exponential form or log, and then your answer. So this extra mark is coming from you showing them an expansion of what this looks like. So in other words, you need to show them what term 1, term 2, and term 3 are going to be. Okay, so you can easily do that by taking your formula and substituting. So for term 1, we would just substitute. We'll take this formula as it is. You can just punch it into the calculator. It is -8 multiplied by 0.5 raised to the power of k minus 1. So in place of k, you see that we started at 1. So you put 1, then minus 1. So our first term is just -8. Then the second term is you're going to substitute in place of k 2. Okay, that is -4. Then the third term, in place of that, you're going to substitute 3, which is -2. So that's where your 1 mark is coming from for expanding. Okay, now we actually have to find the value of m. So look at the way this looks. In order to find the value of a and r, you can see that a is clearly just -8. And r, if you like, you could have said this divided by that, or the third term divided by the second term. But it's not really necessary, because if you look at this formula, it's in the form of a multiplied by r raised to the power of n minus 1. You see that it looks exactly the same. That's why that is the a value, the first term, and that's why this is supposed to be r. The ratio is 1/2. You could have also divided and you'd have found that. Okay, so now that we know what all those are, how do we find the sum of the series? How do we find m really if the sum of the series is equal to this number? So I'm only going to explain this because it is necessary. In this case, it's not really needed, but I'm still going to explain this. You see, since we are working with sigma, sigma is speaking about the sum, meaning we're using a sum formula. Because r is less than 1, I'm just going to use this formula. Even if you use the other one, it's fine. Sn is equal to a multiplied by, and I'll say 1 minus r raised to the power of n over 1 minus r. Even if you use the other formula with r to the power of n minus 1, it would work. But I just want to explain something about this m. You see, whatever number you have here, that's where your pattern will start. And whatever number you have here, that is where your pattern will end. Now, n is specifically speaking about the number of terms that you have in your series. I'm saying this because this may work out, right? We may just work out this as if it is m. But there are other situations where this is a bit different, okay? N is speaking about how many terms there are. M in this situation is speaking about where your terms end. It's not always the same thing. They're not always the same. And let me give you an example of that. If you have the sum where k starts from 1 and the last term is 5, how many terms do you have in this series? In this series, you would have term 1, 2, 3, 4, 5, which is 5 terms. But what if you had again the sum, but k is starting from 0 and you're ending at 5? Now how many terms do you have in this series? You have 0, 1, 2, 3, 4, 5. That's actually 6 terms because k is equal to 0 is also a term. Okay, so that's why I'm saying you need to be careful. So now do you see what you really have to be careful about is this. You have to be careful to check that k actually starts from 1. Then you can just safely say, okay, so whatever number I have here is literally my number of terms. So do you see that here k starts from 1? So we know that m is where we end and also the number of terms that we have. So I'm going to say S of m is equal to, what's our a value? It's negative 8. So negative 8 multiplied by 1 minus our ratio is a half. So 1 over 2 raised to the power of n is what? That is m. So I'm substituting that there. And then over 1 minus our ratio is a half. Now S of m, the sum of the number of terms here, we actually have that value. It is negative 255 over 16. So in place of S of m, I'm going to say negative 255 over 16 is equal to. So here, for the sake of, because this is a video, I'm just going to simplify like on screen where I see things. I see that on the denominator, I have 1 minus a half, which I know can simplify to a half, right? And I also know that if I say negative 8 divided by a half, you can't put that on your calculator. That's going to give you negative 16. Then I still have my bracket, 1 minus a half raised to the power of m, and then close bracket. And now that we have this, in order to get to m, what we're going to have to do is get rid of the negative 16. So we're going to divide both hand sides by negative 16. So here we can just say divided by negative 16. And then what's going to happen on this side is this. You see, we're dividing by negative 16. It's the same thing as multiplying by 1 over negative 16 because of tip and times. So 16 times 16 is 256. Remember that these are both negative. So when they multiply, they will become positive. So our answer here will be 255 over 256. And this is equal to 16 cancels here. And now you have 1 minus 1 over 2 raised to the power of m. Okay, then we can just go ahead and take this over because it's negative. So it becomes positive when it comes over. It's positive. A half raised to the power of m is equal to, and now we still have the 1 here. Then we can take the 255 over 256 over, and that becomes negative 255 over 256. And if you subtract that, you see this is 1 minus that. You can use a calculator, but I can just rewrite that as 256 over 256. That's 1 still. And then it's going to give us 1 over 256. And so now we have 1 over 2 raised to the power of m. Okay, so you see now that this is an exponential equation where we have to solve for m. So to solve for m, to solve for the exponent, you need to make the basis the same. So with the basis being the same, the 1 doesn't have a problem. 1 and 1, they're the same. The only one that has a problem is this. How do we make 256 a base of 2? So we will do that by saying on your calculator, you can say 256 is equal to, and say shift and factorize just so that you can see what it is. It's 2 to the power of 8. So it means that 1 over 2 all raised to the power of m is equal to 1 over 2 to the power of 8. But here's the thing. You can also write 1 to the power of 8 and it will still remain 1. So I didn't change the value. I just changed the way it looks. And since they both have an exponent of 8, you can write that as a fraction raised to the power of 8. And now you see the bases are the same. And so now that the bases are the same, you can go ahead and equate the exponents. So that just means that m is finally equal to 8. And that is our answer. Okay, so given this series that we have where x is not equal to 0, so it's in terms of x, and we have 3.3.1 saying determine the value of x for which the series converges. Okay, for a series to converge, it's first of all, it has to be geometric. So when a series converges, it really just heads towards a specific number and doesn't go beyond that number. And a brief explanation of that is if I take 10 and then I multiply it by half, it's 5. And then I multiply it by half, then it's 5 over 2. And then I multiply it by half. It just keeps getting smaller and it doesn't actually become 0, because that's like taking a slice of bread and you keep cutting it in half and you keep cutting it in half. Even though you keep cutting it in half, it's never going to just disappear. It may end up being a piece that is so tiny you cannot see it, but there isn't nothing there. It doesn't disappear. So that's what I mean by the series heads towards a specific number. In this case, this is heading towards 0. It's getting smaller and smaller and heading towards 0, but it doesn't become 0, and it will never pass that number 0. It will never be lower than 0. Okay, so that's really what a brief explanation of what it means for a series to converge. But in order for a series to converge, the values of x for which the series will converge, for a series to converge, the ratio needs to be greater than -1, but less than 1. So clearly here, the thing is we have to find exactly what that ratio is. So how do we find the ratio here? You can say term 2 divided by term 1. The ratio being 12 divided by 24 over x. So because we have division of fractions over fraction, you have to use tip and times. So I'm going to say 12, and I can put that over 1, of course. And I'm going to tip this. So I'm going to swap the numerator and denominator, making it x over 24, and change the division into a multiplication. Now that I'm multiplying, I see that across I have common factors. So 12 and 24, 12 is common in both. So I can divide 12 by 12. That gives me 1. 24 divided by 12 gives me 2. That's what's left there. So it means that here we have 1 times x, which is x, and 1 times 2, which is 2. So our ratio is x over 2. You can confirm it by also saying term 3 divided by term 2, which is 6x divided by 12. You see that between 6 and 12, 6 is common. So 6 divided by 6 is 1. 12 divided by 6 is 2. Again, you see that you get 1x, which is just x over 2. Okay, so we can see that that is still our ratio throughout. So now that we have the ratio, we can substitute it into this inequality, because this is the inequality that tells us for which the values of x will converge. So that is x over 2 is greater than -1, but less than 1. Now, you need to solve for x. You need to determine the values of x, not the values of x over 2. So this 2 needs to leave. How do you get the 2 out of the denominator? Well, the x is dividing by the 2. So to get rid of the 2, you need to multiply by 2. Do the opposite. So this is an inequality that has 2 sides. Okay, so what you do on this side, you must do on that side. So times by 2 and times by 2, and that will get rid of that problem. So now the 2 is gone and we have an x being greater than 2 times -1 is -2, and 1 times 2 is 2. So x just needs to be greater than -2, but less than 2. Okay, so that is for 3 marks. Moving on to the next question. And then the last question in question 3.3.6 says, write down the value of x for which the series is increasing. Okay, so we're looking at the series now. And the previous question, we found the values of x for which the series converges. So do you remember when I explained that converging series is the series really heading towards a particular number, right? In the case of where r was equal to a half, we saw that that pattern just kept decreasing and decreasing and getting smaller and smaller, and it was heading towards zero. But the thing is that it's never actually going to become zero. Just like if you took a loaf of bread and you kept cutting it in half and cutting it in half, it doesn't eventually become zero. It doesn't disappear. Even if you end up with a very small piece, it's still there. So you see that when it's converging, right, in this situation, that it keeps decreasing, heading towards zero, okay, heading towards being nothing. So for it to increase, this is what we're going to do. We're just going to do the opposite. Since the values of x for which this series converges, and it converging is actually making it decrease and head towards zero. For it to increase, it must do the opposite. So since our inequality says x needs to be greater than -2, we just need to make x less than -2. And here our inequality says that x needs to be less than 2. So we just need to make x greater than 2. And that would be our answer. X needs to be less than -2, or x is greater than 2. Okay, so that is the end of question 3. It's a total of 14 marks. And then we move on to question 4, which is on Euclidean geometry. Okay, grade 12. So now we are on question 4. And question 4.1 says, given we have triangle ABC and triangle DEF with angle A being equal to angle D and angle B being equal to angle E and angle C is equal to angle F, you need to prove that AB over DE is equal to AC over DF. Now, I have a proof on this on KZN's 2020 paper, okay, the March 2020 paper. So I actually want you to go ahead and look at that paper, and I'm going to link the paper in the description. I want you to go ahead and look at that part of the proof, and then I want you to come back to this paper and then attempt to prove this one by yourself. Okay, so with that being said, moving on to 4.2. Okay, so question 4.2 says, in the figure, we have AD, DC, and BE are tangents to the circle at A, C, and B respectively. So you see, look at the tangents that we have, right? And BE, of course. Then they tell us that O is the center of the circle, DE and AF intersect at H. Then we have AH produced meets BE produced in F. And then, of course, AJ, BC, and BJ are chords, so those are just chords. The first question is we need to prove that triangle DAH is similar to triangle OCH. Okay, so now that we have highlighted the two triangles, do you see that they are sharing one angle here? They have a common angle H2, so we know by default that's already equal, okay? Because it's a shared angle. So it means we just need to find two more angles, or really just one more angle, because the third angle in the triangles and two triangles are going to be equal as well. So this is what we can do. You see, the order in which they named the triangles is very important. These triangles, their angles will also be equal in that same order. So if we have DAH, D is the first letter, it probably means that angle D in that blue triangle is equal to angle O in the yellow triangle. So it means this is probably equal to O2. Now you can look at those for a while and just see how can they be equal, because I'm not saying they're equal yet. You have to prove that they're equal. So I know that this is supposed to be equal to this. And if you look at that for a while and you can't see why those two are equal, that's okay. Move on to the next letter in both triangles. So I tried D and O, I couldn't really see it. So let's try angle A in the blue triangle and angle C in the yellow triangle. So angle A is this angle here. Angle C in the yellow triangle is this whole angle here. How can those be equal? Can we even find the values of those angles? Well, do you remember that AD is a tangent, right? And this OA is a radius. The radius is always perpendicular to the tangent at the point of contact. So if this is 90 degrees, let's try and find this one. So this angle, do you see that we also have another tangent here as well? And OC is also a radius. The radius is perpendicular to the tangent at the point of contact. So there, that's also 90 degrees. So do you see why those two angles are equal? So now we can go ahead and start writing. So we say in triangle, and we're going to name them both DAH and triangle OCH. The first one that we have is, we're just saying the common angle. H2 was equal in both triangles because that includes angle H2. That also includes angle H2. It's a shared angle. So I'm saying angle H2 is equal to angle H2. And I'll say it's a shared angle. You can also say common angle. And I'll use the symbol for angle. Then the next one that we know is equal is this one that we just found. So we'll tell them that this angle, I can't call it angle A because you just have to name it really. I'll just call it angle HAD or DAH. So angle DAH is actually going to be equal to this angle OCH, that 90 degree angle, equal to OCH. And I can also further say that they're both equal to 90 degrees. And the reason they are both equal to 90 degrees is, do you see? That's a tangent being perpendicular to a radius. So you say tangent perpendicular to radius. Okay, so there we have another angle that is equal as well. Just remember it is an angle that we have there. Okay, so because you have now two angles in the triangles being equal, by default the third angle is equal. If you have two triangles, and this is equal to this, and that is equal to that, by default, these two must also be equal because the angles in a triangle add up to 180 degrees. So we just have to name the third angle. The third angle here is this D, which we can call angle D. It's just on its own. So I'm saying that angle D is equal to what angle in the yellow triangle? The third angle in the yellow triangle is this angle, angle O2. Angle D is equal to angle O2. And the reason why is because it's the remaining angle. You can say that, or you can say third angle in triangle. And so we can conclude, therefore, triangle DAH is similar to triangle OCH. And our reason is because angle, angle, angle. Three angles are equal. Okay, so that is for 4 marks. Moving on to the next question. Okay, 4.2 says we have OH is equal to, we need to prove that OH is equal to AO multiplied by DH over DC. Whenever you see them start putting letters down, you need to see where these letters are coming from. Now, because the previous question, see this is 4.2.2, but this is 4.2.1, it means that this question has a lot to do with your previous answer. In the previous question, we proved that triangles were similar, okay? So in this question here, it probably has a lot to do with these. So what I'm going to do is I'm going to take these so that I can find the proportions of that triangle. What is equal to what? What is in proportion with what? So this is how we do that. I don't even need the triangles to do that. I just need the structure of how the triangles are similar to each other, like this really. So what we can do here is say, see DA, that we can put that over OC. So you see first and second letter, first and second letter. It means they're in proportion in this way. So over OC is equal to, and then here I can say is equal to AH over CH as well. Second and third letter in both triangles. So AH over CH. And that would be equal to, lastly, the two letters that we can put together, two sides that we have DH over OH. Now, I'm going to look at these proportions and I'll say that, of course, this is because of similar triangles. Now, I'm going to look at these proportions and see from these proportions what is being represented here. Okay, what do we have here? Firstly, I see OH. That's great. So it means OH is probably going to be included. I also see DH. DH is also included. So this proportion here is going to be included. But then I'm seeing OA and DC and I'm not sure where they come from. And this is where I go back to the diagram and I start seeing how is it related. Okay, so OA or AO, right? And DC. Let's look at AO first. What is AO? AO is a radius. That's a good thing. AO is a radius, but we also have other radii in this diagram. Another one, really, not other ones, just one more. We have OC. So it's probably a situation where they replaced OC with AO. So I'm going to go back there and I'm going to see if I replaced OC. Do you see that we have OC here in one of the proportions? If I replace that with AO, that's going to work perfectly, okay? So it means that this was actually OC. They just replaced it with AO because they are exactly the same length. So it means that I can take that as a proportion. And now I can try and find out, where did DC come from? Okay, so let's look above and see, where did DC come from? Well, DC is this, okay? It's one of the tangents. And do you see now that DA, the one that we have here, the proportion we have here, DA, is also another tangent. What do you know about tangents drawn from the same point to a circle? That they are equal. So it clearly means that they took this exact proportion, this whole thing. They just replaced DA with DC because they were equal. And OC, they replaced it with AO because they were equal. So this is what I'll do from here. I'm going to take these two proportions. I'll say, therefore, I'm saying that DA over OC is equal to DH over OH. Then I can go ahead and tell them I'm going to create this like this. I'm going to also do that. But I know now that DA is equal to, and I can see here DA is equal to DC. So wherever I see DA, I'll replace it with DC because I see that that's what they did. So it's equal to DC, and I'll give my reason. That's because tangents drawn from the same point to a circle are equal. Okay, so now we have DA and DC. I know I will replace that. The other issue was OC that I had, right? So I'm going to replace OC with what they replaced it with. Well, seeing that they're equal, OC is actually equal to OA. So I'm going to replace that and say that here, OC is equal to OA because they are equal radii. So equal to OA because of radii. If you like, you can say equal radii. It's still fine, but radii is also okay. Now that I know that these are equal, I'm going to rewrite what I have here, but I'm going to replace DA and OC. So it means that therefore, instead of having DA, I'll have DC. DC over, instead of having OC, I have OA. OA is equal to, then I have DH over OH. That one was not a problem. And now I just have to multiply or divide and just see what do I have to do to just get it to look like this, okay? So I see that first of all, OH is on its own. That's what I have to think about. How do I, in this, get OH to be on its own? Well, OH is on the denominator right now. So the first thing I would do is just cross multiply so that I can get everything to just be spread out. So I'll cross multiply. DC times OH is just DC times OH is equal to, and then OA times DH is OA times DH. Remember, the goal is to get OH to be the subject of the formula like they have there. So to get OH to be the subject, what you have to do, you have to get rid of DC. So divide both hand sides by DC. And when you divide by DC, you see that OH is actually just equal to OA multiplied by DH over DC. And now do you see that that's what they also have? AO, which is OA, still the same thing, multiply by DH over DC, and we have proven that. Okay, moving on to the next question. Okay, so question 4.2.3 says, if BA is drawn, then FB squared is equal to JF times AF. Okay, so let me take this to the top. Let me pin this to the top so that we can see which size they're speaking about. Okay, so if BA is drawn, so let's actually draw BA. BA is like that. So if BA is drawn, you need to prove that FB squared is equal to JF times AF. So where is FB? FB is over here. So we have FB, and let me use different colors for that. So FB, right, is that. And then we have JF, right? JF is that little part. and we have AF. So if you look at this, it looks like they're speaking about two triangles. Okay, it looks like this triangle, which I'm highlighting in purple now, this little triangle here, BJF, because the sides BF and JF are in these dimensions that they're asking for here, right? And then the other one, remember we have BA. They said if BA is drawn. So clearly BA has a lot to do with our answer. So we have BA and they mentioned AF. So it's this purple triangle, and let me highlight the other one in, let's just say, green, right? So the other triangle that they seem to be speaking about is this triangle, also including BF. And they seem to be using their dimensions over each other and then they multiply through. So this is probably a case where these two triangles are similar and you see that they're sharing an angle. They have a common angle. So one angle is already the same. So it's probably a case these two triangles are similar and then we can use their proportions over each other. So let's try and prove that these two triangles are similar. Okay, so in naming them right now, naming them may not be that simple, but I'll name them in any order and I'll show you that you can still end up naming them correctly. Okay, so I think this is a perfect question for this. Okay, when they don't name the triangles for you, how do you do that? So I pinned it to this side just so that we can look at it easily. So I'm going to name the triangles and I'm not going to name it properly because right now I don't actually know what it should be named. So I'm just going to name it anyhow. And I'll show you that you can still end up naming it correctly based on how you find your angles. So first triangle, I'll just say in triangle and I'll name it anyhow. I'll just call it ABF, right? ABF and triangle. The other one, I'll just call it BJF, okay? BJF. And I don't know if it's in the correct order. I'm just naming. Now let's focus on the angles that are equal. If three angles are equal, the triangles are similar. So we had a common angle, F, right? And we can just call that angle F because you can see it's not like angle F, then we have a little angle here. It's just angle F on its own. So angle F is equal to angle F. And I'm just going to say because that is a common or shared angle. You can say common, shared, it's still fine. Shared angle. Okay, then the second thing, let's look at what else is equal in the green triangle and the purple triangle. Okay, so looking at this, what I see in these two triangles, I have to look at angles in the triangle and see how are they equal to each other, the purple and the green triangle. I'm noticing that here I have a tangent BF. The angle between the tangent and the chord is always going to be equal to the angle supported by that same chord. But remember that angle must be at the circumference. So do you see now that angle A is actually equal to angle B2? So angle A equals angle B2. Here's the thing about being able to name these triangles properly. And this is what I should have mentioned at first. If I didn't name it properly here, it's okay, right? I have to name it properly in the conclusion, but finding the angles will help me do that. What you need to do is make sure that on this side, the angles that you are writing here are the angles that belong in this triangle that we have, triangle ABF. So I'm going to make sure that now with the F, that's not really going to be a problem. Triangle ABF is the bigger triangle. And then just remember the other one is the smaller triangle. That's the smaller triangle. So make sure that we're going to just do that. That's what I'll just do first of all. So angle F, that's not a problem. But now I'm saying these two angles are equal. I remember that the green triangle, right? That's the one with angle A. So I'm going to put angle A on this side. I'll show you why I'm trying to keep it like that. So green angle from the green triangle must be in the green triangle's column. And that is equal to, okay, I have to name that properly. I can't call that angle A. I have to call it angle, let's call it BAF because you see there's also another angle A. So let's call it BAF, but I remember that A is the reference angle. And it's equal to, or the focal angle. And then that is equal to this angle over here. And there's no confusion there. It's just angle B2, equal to angle B2. Okay, so that's the green side. Okay, and our reason for that is because of the tan chord theorem. So tan chord theorem. And now that we have that, by default, when two angles in the two triangles are equal, by default, the third angle will be equal. So we just have to name that third angle. We mentioned F, we mentioned these two. Now look in your green triangle. Which angle did we not mention? The only angle we didn't mention is this bigger angle. And I'll call that ABF. Okay, so that is ABF, focal angle is B, is equal to which angle in the purple triangle did we not mention? That's this angle over here, J, but I can't just call it J, I have to name it. So BJF. So it's equal to BJF. And I'll say that is because it's the remaining angle. I can say that. Or I can say sum of angles in a triangle. Or I could say third angle in a triangle. Okay, so there we got three angles being equal. And now look at where you conclude and why I said it's not really important to introduce your triangles in the correct order, because sometimes you don't know the order, like this one. Okay, so here's how we conclude. We say, therefore, triangle, and I'm focusing on the green triangle. I will just look at all the focus letters or the focus angles in each of the triangles. You see, I see F. Here, the focus angle is the A, and here the focus angle is the B. So I'm going to call that triangle FAB. That it's similar to, and I'm going to do the same thing in the other triangle. So the other triangle, we have F, and we have B as the focus angle, and then that J. So it's similar to triangle FBJ, and now it's in the right order. Now I can actually use those proportions over each other. And the reason, of course, is angle, angle, angle. Okay, so how they got this? It's from the proportions. So I'm going to take the proportions over each other. Let's start with FA. So we'll say FA over FB, first and second letter, is equal to AB over BJ, sorry, which is equal to FB over FJ. Okay, so in that order, first and first, second and third, and then first and last. And you must do the same on both sides. And this is because the triangles are similar. Okay, so you can say similar triangles. We can say those proportions are like that. And now that we have those proportions, I'm going to again look at this and see what is repeated here that is also here. Okay, so the first thing I see, let me look for BF. Do I have BF, or it can also be FB, of course? Yes, I do. I have FB. There it is. And then you see that we have FB squared. So that's an FB times an FB. I also have another FB here. Okay, so those are two that are there. Then we have a JF. JF, we actually have that here. That's FJ. And then we have an AF. We have that FA. So you can see it's this over this that they use. So now I can conclude that FA, or let me actually write it in the same order that they did. So instead of calling it FA, I'll call it AF over, and I'll just say BF is equal to this BF over, and I can call this one FJ, I guess. JF, they called it JF, so JF. Okay, so now that I have that, I'm just going to cross multiply. So the BF multiplied by the BF gives you BF squared. And then the AF multiplied by the FJ is just AF multiplied by JF, right? So there, do you see that it's exactly the same? If you like, you can make sure you can just switch them around. They're still going to be the same. So I can just rewrite that as JF times AF. So there, and that's how we get that answer. Okay, so that is the end of question 4, and it's a total of 23 marks, and we move on to question 5. Okay, so now we're on question 5, and question 5 says, in the figure, AF is equal to 2CG. Okay, so those are just proportions that they've given you. And then they tell us that FE is parallel to GB, and we're also given that AE over AB is equal to 2 over 5. So that's AE over AB. Okay, so what I like to do is when I see they give a ratio, I like to just put it down. So AE instead of calling that 2, so I don't get confused and think that this is actually the length, it's not the length, it's the ratio. Meaning this length could have been something like, let's say 4, and then this could have been a length of 10. If you say 4 over 10, it will simplify to 2 over 5, you see. So it's just the ratio at which those lengths are being shared. So I'll just call this 2k so I don't confuse myself. I know it's not a length. And then AB, I can just go ahead and call that 5k. Okay, so that can already show you what EB is going to be. But the first question is you need to determine AF over FG. So do you see AF over FG? Because we are given that these two are parallel, and we know what AE over AB is, we can find AF over AG, really. But because they want us to find FG, we're going to have to find that. But this is how I'll go ahead and just do this. Just find EB, right? You can see that this is 2k, so it means this must be 3k for us to get 5k. So to name these sides and to just tell them what they are, I can just go ahead and tell them, let's just say AE is 2k. And it's fine to say that because if you say AE is equal to 2, you're literally saying that the length of AE is 2, and it's not. So if AE is equal to 2, then that would mean that AB, so 2k, sorry, AB is equal to 5k. So I'm really just saying what I wrote down here. And if that is the case, then it means that EB, you would find it by saying AB, which is 5k, minus AE, which is 2k. And so we know now that EB is equal to 2k, right? 3k. Okay, so now that we know that this is 3k, we can find this. Do you see that we have parallel lines? So it means that if we found AE over EB, we'd be able to find AF over FG because these two lines are parallel, and so therefore those sides are in proportion. So this is how we're just going to tell them, because we're trying to look for this, right? So I'll always keep that as the subject of the formula. I'll say that AF over FG is actually equal to, now I took AF, so I need to take AE, right? The one that is in line with it, the same side in line with it. So AE over, and that is EB, because FG, right, the one in line with it is EB, so over EB. Now I know what these proportions are, so I'm saying therefore it means that AF over FG is equal to AE, the ratio of that is 2. So I can just say 2 over EB, the ratio of that is 3. Even if you put it in terms of K, do you see that the K's would have still cancelled? And that's why I left it like that. And so there, that is our proportion. But I forgot to say here, when you use proportions, as you can see, we use one hand side and say that those proportions were equal to the other hand side. You need to give a reason. And you can't say proportionality theorem. Actually, I'm not sure if you can say proportionality theorem, but the reason is usually because we have a line drawn parallel to one side of the triangle. Okay, so it's really just saying there is a line drawn parallel to one side of the triangle. Okay, so now that we have that, because I have AF over FG, I would also like to name them. I know it's 2 over 3, but I'm just going to put them in terms of another letter, so I know that I'm talking about another side. Okay, it's not the same side. So that AF now, right, that's 2. So I'll call that 2A. AF, I'll just call that 2A. And then FG, I can call that 3A. Okay, since it's 2 over 3. So just keep putting those there so I don't forget. So the next question, 5.2, we need to determine CH over HE. CH over HE. Let's look at that. So CH is over here. And we need to get that over HE. Over HE. Okay, so I see one part of it that we can find. We can find HE. Okay, we can find that because do you see that HE is perfectly in line with FG, right? Because you see the parallel lines. The only one that we don't know is this. We cannot really find CH right now because we don't know what CG is. So because we can see that this is coming from the same line, in order to be able to find, CH, you need to find CG. So how do we find CG? Well, it's best to find CG and it needs to be in terms of A, because either ways you're going to have to say, because if you look at this upside down, that's really how you'll see it. You see a triangle, two parallel lines. For you to be able to say CH over HE, right, is equal to CG over GF, you need this to also be in terms of A, like that one, because of this. So how do we get this in terms of A? So the only issue right now is what is CG. But if you look in the scenario, you see that they mentioned something about CG. So that's a good thing. They mentioned something about CG. They tell us that AF is equal to 2CG. So let's use that. Okay, so since AF is equal to 2CG, let's just figure out what AF is so that we can find out what exactly CG is, because we need that. What is AF? We have 2, right? Now in the diagram, I called AF 2A. I'm going to just first of all tell them I'm going to let AF be equal to 2A. Okay, so I'm still saying the ratio is 2. I'm just naming that side, that part of that line A, right? So if this is the case, then it means that I'm going to substitute AF into here, which is 2A, is equal to 2CG. Then if you divide both sides by 2, we finally find out that CG is equal to 2A divided by A is A. So that's what I can call CG now. So look at what I'm doing. In the diagram, it means that CG, that part is just A. And now I can finally find out what CH over HE is. So if you look at this again upside down, you see a triangle, 2 lines being parallel, okay, in that triangle. So it means that CH over HE is equal to CG over GH. Okay, and instead of calling it GF, I'll just call it FG because that's what we really had there. Okay, and the reason for this, the reason for those lines being equal to each other is because we have one line being parallel to one side of the triangle. In other words, the proportionality theorem. That's the reason why. So now we can finally say that CH over HE is equal to, and then what are those proportions that we have? The proportions we have for CG and FG is A and 3A. So that's A over 3A. That's what we have there. So I'll just say that is A over 3A. Which, if you see how that works, that simplifies. It's just going to simplify this. So this CH over HE, it simplifies to, if the A cancels, you're left with a 1 here as a coefficient. So that's just 1 over 3, and that's your answer. So you see, the key thing is when you have one line, you need to make sure that they're kind of named in terms of the same variable. They're all ratios, but when they're named in terms of the same variable, then it means that they're being shared in the same way. Like A stands for one specific number. So 3A is 3 times that number, and 2A is 2 times that number. Okay, so we'll move on to the next question. And then the last question in 5.3 says we need to determine the area of triangle BCG over the area of triangle AFE. So let me pull down what we have in the diagram. Okay, so there are various ways to find the area of a triangle. If you had a height, a perpendicular height, right, then the area will be a half times the base times the height, that perpendicular height. But as you can see in these triangles that they're mentioning, we don't have a perpendicular height. And let me actually just highlight those triangles. The triangle that we have first of all is triangle BCG. So BCG, that triangle. And the other one is triangle AFE. So triangle AFE, that triangle. We have to find the areas of those triangles over each other. You have to individually find the area of each triangle first. So the alternative way of finding the area of a triangle is by using something called the area rule. So when you have a triangle, and let's say you've been given this as ABC, right? Let's say you've been given the angle A and the side AB and the side AC. You find this by saying a half multiplied by AB multiplied by AC, and then sine of angle A. That's how we find the area of a triangle. That's the second method using trigonometry. So that's what we're going to use here. And the reason we're going to use that here is because you see these triangles, they have sides. Yes, they're not the lengths of the sides, but they're their ratios. And that's perfect to use here because you're dividing over each other. Okay, so we're going to use it like that. So do you see for this triangle AFE, right? That one is not that difficult to find. As you can see, we have our angle, the middle angle, sine of A. Yes, we don't have an actual number, but that's not a problem. We have AF and we have AE, right? So we can actually find the area of that. And of course, we're going to have sine A next to it. So when finding the area of this triangle, we kind of also have to find it, but it needs to be in terms of sine of angle A. Because if you just found it like this and said, oh, it has one side here, then we don't know what the side is. And you can't say over sine of angle C, because then they will not cancel, they will not simplify. What we're going to do is try to find the area of this triangle, but it has to have something to do with sine of angle A. Okay, so you see for this one, we can actually find the area. It's this one that we're looking at now. So to find that in a way that it's going to have sine of angle A, think about it like this. If we found the area using trigonometry of this entire triangle, we would be able to find that, because do you see that the area of this triangle ABC, right? We have angle A there. We also have this entire side. It's made up of 2A plus 3A plus A, which is 6A that we have there, right? And we also have this side as well. So we can find the area of that. If we find the area of that, and remember, the whole goal is to find the green one. If we find the area of that big triangle and we subtract it by the area of this triangle, right? So taking this big piece minus this one, what are you going to be left with? The area of this green triangle. It's like a piece. We're taking that big piece, right? Minus that piece. And so we end up with that triangle. That's what we're going to do. So to construct a way to find, well, I'll just put them over each other. Let's start with that BCG. So in order to find BCG, I'm going to take the area of that bigger triangle. So I'm going to take the area of triangle ABC, that big triangle. And I'm going to subtract it by the area of this triangle, which is ABG. Okay, minus the area of triangle ABG. And then I'm going to put that over the area of this triangle, which I can find because I have its sides. Okay, so over the area of triangle AFE. That's what I'm going to do. Okay, so let's start with that area of triangle ABC. How do we find that? Area of triangle ABC can be found by saying a half. So let me actually just put that in a specific color just so that we remember. So that's going to be in red. The other one can be in blue. This one can just be in blue. And then I'll leave that in black. So the area of triangle ABC is going to be, we're going to say a half first, then multiplied by the first side, the one side of AC, multiplied by the other side, which is AB, then multiplied by sine of angle A, sine of angle A. So I need to put them in terms of the same angle, really, just so that they can cancel at the end of the day. Then I'm saying that is being subtracted by this one, the area of triangle ABG. So that is a half again multiplied by, so we can see ABG multiplied by AG, that's one side, multiplied by AB, that's another side. Then I have to say sine of, it's also sine of angle A. I'm using angle A as the middle angle, angle A. Then I'm going to put that over triangle, area of triangle AFE. And that's going to be a half multiplied by AFE. So it's just AF multiplied by AE. And then sine of the middle angle again is angle A. So you see they're all in terms of sine of angle A, which is great because it can eventually cancel out. Okay, so now that we have this, we're saying is equal to, and then we still have a half times what is, I realized that's supposed to be AC. I don't know why I said A. It's AC, right? So I'm saying a half multiplied by what is AC. Half times AC is that whole length of 2A plus 3A plus A, which is 6A, okay? Multiplied by, and you'll see the A's and the K's will cancel out. You just have to put them in terms of something. It can be A and B. It's still fine as well. Okay, so then we have times AB. So times AB, which is made up of 2k and 3k, but you can see the total is 5k. So times 5k sine of angle A. Then minus, and again we have a half, times AG. AG is 2a plus 3a, which is 5a, multiplied by AB. And AB, as you can see, that is 5k. Then we have sine of angle A over, and then a half multiplied by AF is 2a, multiplied by AE is 2k, sine again of angle A. And now it just has to do with simplifying. Okay, so if you simplify that top, a half times 6a is 3a, times 5, 3 times 5 is 15. So what we will have there is 15ak sine of angle A. Then we have minus, and then we're also just going to calculate here. I'll just say 5 times 5 is 25, times a half is 25 over 2. Then I also have AK sine of angle A. You see they're in the terms of the same thing. That's what we're trying to make. Okay, then this goes over what we have on the denominator, which is a half times, okay, 2 times 2 is 4. 4 times a half is 2. So that's 2AK sine of angle A. And now that's like terms. So we just simplify. What is 15 minus 25 over 2? So 15 minus 25 over 2. That gives us 5 over 2. So on top, we have 5 over 2 first. So that is 5 over 2. Then AK sine of angle A. That's what that part simplified to. And then that is all over 2AK sine of angle A. And now do you see that A and K will both cancel, and sine of angle A cancels. All you're left with is what is 5 over 2 divided by 2. You can tip in times and you'll find out that it's going to be 5 over 4. So that is what those areas put over each other would give us. Okay, so that is of question 5, and we are done with Euclidean geometry for this paper, and we move on to question 6, which is on trigonometry. Okay, so question 6.1 says, given cos of 26 degrees is equal to 1 over p, without using a calculator, calculate the value of the following in terms of p. And the first question is cos of 52 degrees. So you see when you get something like this, cos of an actual angle, an acute angle, most of the time it's an acute angle, and then you have some sort of variable, right? So you have 1 over p here. This is a trig diagram, and this is how it's drawn. You see that it's saying cos of 26 degrees. Think about which quadrant 26 degrees will appear in. It's an acute angle. If I measure 26 degrees, that is 26 degrees. So it means my terminal arm, or my radius, is here. Okay? So there I can also just move it down to the x-axis, and it's perpendicular to the x-axis. So this is what we have. And they said specifically cos of 26 degrees is 1 over p. Well, what do you know about cos? Cos says what over what? It says adjacent over hypotenuse. So 1 is your adjacent side, and our adjacent side is here, this side, the side next to the angle. So 1, and then the hypotenuse is p. So you see that the opposite side is what we just have to find in this question first. So to find the opposite side, we can just call that y. You see, this is called x because it's literally the x coordinate, okay? It's on the x-axis. This is our radius, so we actually call it r. And so this is a y value. If you look on the y-axis, whatever number is here, that's that y value. So we call that y. So we just need to find y. Y we find by saying y squared is equal to, and now we're just using Pythagoras. Since we're just looking for one of the shorter sides, you must always say the radius or the hypotenuse squared minus the other side squared. So that's p squared minus 1 squared. Okay. Then you can square root both sides to find y. Now, we usually put a plus and minus here, but you see that we're in the first quadrant. So everything here is positive. Y, p, and x is positive. So we have y is equal to, that's actually r. Y is equal to, now we have the square root, positive square root of p squared, will just stay p squared, minus 1 squared. If you square 1, you still get 1. Okay, it's not negative 1 squared. They didn't do this negative 1 squared. Okay, it's minus and then 1 squared, which is just 1. So y is equal to p squared minus 1. That's what we have there. That's square root of p squared minus 1. Okay, so the first question is actually asking us for this. We need to find cos of 52 degrees. Now at this point, you're just going to constantly think about the angle they gave you and how does this angle relate to 26 degrees. So if I look at 52, it looks like double of 26 degrees. So look at how I can rewrite that. Cos 52 degrees, I can rewrite as 2 times 26 degrees. And now do you see that this is a double angle, cos of 2a. So you can change it into any one of the double angle formulas. I'm going to specifically change it into 2 cos squared of a. So my a is 26 degrees minus 1. Okay, so now that I have this, I just have to find out what cos of 26 is. I'm saying 2 multiplied by cos squared of 26 degrees. So whatever cos of 26 degrees, I'll find that and I need to square that. Then of course minus 1. So we just have to find what cos of 26 degrees is, which we already know from the beginning. It's 1 over p. Okay, so you see, choose the one that would be in your favor. I chose that because I had cos. So that is 1 over p. Okay, so that's 2 times 1 over p all squared minus 1, which is 2. And then we need to square that. So 1 squared is 1. P all squared is just p squared. And then we have minus 1. So what is 2 times p squared? Well, 2, you can write it as if it's over 1. These two are multiplying. So numerator times numerator and denominator times denominator. Then minus 1. And that's really just our answer. Okay, moving on to the next question. Then 6.1.2, we have sine of 71 degrees. Again, we look at the angle and we find out how is this related to 26 degrees. You see in the previous question, it was related to 26 degrees because it was double the size. So that was double angles. But in this one, how is it related? Well, usually when it's an acute angle, my mind usually goes to, okay, maybe this is cofunctions. Maybe these are cofunctions. But the thing is 71 degrees. If you say 90 minus 71 degrees, that is going to give you 19 degrees. And as you can see, 19 degrees is not 26 degrees. Neither does it have anything to do with 26 degrees. It doesn't have anything to do with 26 degrees if you're using trigonometric rules like identities, using special angles, using cofunctions, using reductions. It doesn't have anything to do with 26, so I can't use that. Okay, it didn't work for cofunctions. Now, because I don't want to beat around the bush looking for different things, what I'm going to do is immediately try to see. Let's say I take out the 26 degrees from this angle. What will be left? So I'm going to say 71 minus 26 degrees. And I want to see the type of angle I have. And when I do that, I get 45 degrees. Does that look familiar? That is a special angle. Okay. So clearly we need to break 71 degrees into this. So we're saying sine of, and we're going to break it into 26 degrees plus 45 degrees. That's what gives us 71 degrees because 45 degrees is a special angle. Okay, so now do you see that this is in the form of compound angles? It's sine of A plus B. So the same way you'd expand that is the same way we'll expand this. So this is going to be sine 26 degrees times cos 45 degrees plus cos 26 degrees times sine 45 degrees. Okay, then we're going to just simplify where we can. Sine 26 degrees, we can find that in this diagram. Sine says saw katoa, right? Saw mean opposite over hypotenuse. So taking the opposite side over the hypotenuse. So that is square root of p squared minus 1 over p. So root p squared minus 1 over p. Then this is being multiplied by cos of 45 degrees, which is a special angle. Okay, so now you have cos 45 degrees, and I'm glad for this because now I get the opportunity to show you another method that you can use. So you can use the calculator, but the thing about grade 12 is that sometimes they don't use the calculator. They would use a rule. They would use either the special triangles, they use another rule that gets you to those answers. If you use the calculator sometimes simplifies the answers. So I'm going to introduce a rule here, and it's called the OHA rule. And this is why it's OHA, right? So that's for opposite, hypotenuse, and adjacent. Then we're going to write the numbers 1, 2, 3, 3, 2, 1, and 1, 2, 1, right? Then in each row, we will square root the biggest number. So I square root the 3 here. And in this row, I would square root the 3 here. And in this row, I square root the 2. Okay, then afterwards, we're going to write our angles. The angles go like this. You say 30, 60, 45. They must go like that. So you see, small, big, small. 30, 60, 45. Okay, so this can actually help us to find what exactly those ratios are going to be in your special angles. So cos of 45, because we know cos, the function says ka, which is adjacent over hypotenuse, we're going to go to the 45 degree column, okay, the 45 degree row, and then we're going to take the adjacent side, that is 1, over the hypotenuse, which is the square root of 2. So that is actually 1 over square root 2, okay? That's what cos 45 is. If you use a calculator, it would have given you root 2 over 2. See, if you say cos 45, okay, not this calculator. Okay, it does. It still does that. Root 2 over 2. Because it rationalizes the denominator. It makes the denominator a rational number. Then we say plus, and then I continue here. This is going to be cos of 26 degrees, which we can find. We know that already. That is 1 over p. So that is 1 over p. Then multiply by sine of 45 degrees. Sine of 45 degrees, sine says saw, meaning opposite over hypotenuse. So go to 45 degrees, take the opposite, okay, 1 over the hypotenuse, which is square root of 2. So that's 1 over square root of 2. You see cos 45 and sine 45 are the same thing. Okay, so this is what we have now. Remember that you have an addition sign here. So it means that this is one term and this is another term. So you need to simplify it term by term. So if we multiply, numerators multiply. Anything times 1 stays the same. So on the top we have p squared minus 1 over p times root 2 is just p root 2. Then we have plus, numerators multiply. That's 1 over, again we have p root 2. You see the denominators are the same, so we can perfectly add them and leave the denominator the same. So that square root plus the 1, you can write it as square root p squared minus 1 plus 1. I'll just write it in the way that the calculator normally puts it if these were numbers. I'll put the 1 first. So I'll say 1 plus square root p squared minus 1 over p root 2. So there we go. That's the answer. Okay, so that's the OHA rule that you can use if you didn't want to remember your special triangles. You can just use the OHA rule. It works perfectly. For things like 90 degrees, don't worry. The calculator is perfect for that. It does not change in the calculator, okay, because you don't have any roots with 90 degrees. Okay, so that is the answer. And moving on to the next question. Okay, question 6.2 says simplify without using probably a calculator into a single trigonometric ratio. So how do we simplify this? The first part, you see that we have cos negative 180 degrees. Whenever you have a negative angle, the solution is you need to add 360 degrees to it. So that just becomes, what is 360 minus 180? It's 180. So we have cos of 180 degrees. Then we have times tan of theta. And then we have cos 690 degrees, which is another angle that you need to look at. You see, this is an angle that is over 360 degrees. Now you do the opposite. When the angle is over 360 degrees, what you do is subtract 360 degrees from it. And then what is 690 minus 360? That's going to give you 330 degrees. Okay, then we continue. Here we have sine of, now do you see, look at this. This is not 180 minus theta. This is theta minus 180. If you look at that angle, theta is seen as, in that cos diagram, as an acute angle. That's why it lies here. Everything less than 90. If you had that acute angle and you subtracted 180 degrees from it, that angle is going to be negative. So that is regarded as a negative angle. When you have a negative angle, what do? You add 360 degrees to it. So something you can do to remind yourself is focus on the angle, like the actual number. When you see that that's negative, it's a negative angle. Okay, so that when we add 360, we're going to look at it as 360 minus 180. That gives you 180 degrees. And then we still have a positive theta here, which I'll just say plus theta over, and look at what we have here, cos squared of theta minus 90. Okay, so with this one, you have to be careful. I know many people look at, for example, just the cos of theta minus 90 part, right? And they're like, oh, okay, I can take out a common factor. Not for this one. For the other ones, it works out, but you need to be careful. And that's why it's important to understand how something simplifies rather than just applying rules that feel right. The thing about this is you have a negative 90 degrees. That numerical value is negative. So the thing is your angle is actually negative. So if you add a 360 degrees to this, this is what you'd get. You'd get cos of 360 minus 90 is 270. So we actually have 270 degrees, then a positive theta, right? Now, how do you simplify this? How do you reduce this or, get it to a single trig ratio? This is how we do this. We're going to say cos of 270, and we're going to break 270 up. So it's still going to be cofunctions, but look at how we break it up. I will break 270 up into 90 degrees plus 180 degrees. That's what gives you 270. So you remove a 90 from it, then plus theta. Then I'm going to group these two together. And now I'm going to use cofunctions on this. You see the same way cos in cofunctions of 90 degrees plus a, for example, is equal to negative sine of a. The same way, we're going to use 180 degrees plus theta as if it is our a. Okay, so just change that to red. So think about it, cos 90 plus 180 plus theta, which is our a. If this was reduced to negative sine of a, it means this is going to be reduced to negative sine of, what's our a? 180 plus theta. Okay, and now that we have that, look at what this actually simplifies to. It is actually negative, and then we have to simplify the sine 180 plus theta. In the Cartesian plane, 180 plus theta appears here, and this is tan's quadrant. Sine is negative in that quadrant. So do you see, I'll open a bracket, and I'm saying that this answer simplifies to negative sine of theta. Then if you multiply that in, that is positive sine theta. Do you see why it's dangerous to just immediately take out a common factor and then use cofunctions on that? Because your answer would have been negative, but the actual answer is positive. So for this one, so that you don't get lost, I suggest that you actually study how to simplify your cofunctions. And I'll just write them up here, the positive ones and the negative ones. Okay, so you can just study it like that. You remember. But in this one, you actually have been safe, even if you didn't know that it was going to simplify to that. If you just took out that common factor, you would have actually been safe. And this is the reason why. You would have been saved by the square. Because of that square, it would have helped you. So meaning whatever answer you get for cos theta minus 90 degrees, which we now know is sine theta, you would square that. Okay, and so that of course give you sine squared theta. Okay, so this is equal to cos 180. When you have an angle like this, don't worry, you don't have to really use the reduction. They will not penalize you. You can put that onto the calculator. Okay, so cos of 180, that is just negative 1. So that's negative 1 multiplied by, and we have tan of theta, and then cos 330 degrees. Let's reduce that angle. So remember, 330 degrees is angles that are greater than 270 but less than 360. So that is cos's quadrant. The reduction there is 360 minus theta. So if you say, look at 330 degrees, ask yourself, if you say cos of 360 degrees minus what gives you 330 degrees, that's minus 30 degrees. And if you reduce this, it is in cos's quadrant, so it remains positive. It will become cos of 30 degrees. Okay, then we have this as well. So sine of 180 plus theta. 180 plus theta again is in tangent quadrant. Okay, 180 plus theta, so sine is negative here because it's in tangent quadrant. So it becomes negative sine of theta. Then over that just becomes sine squared of theta. Okay, so this is equal to, now I'm seeing that we have a negative times a negative number. It will just become positive. So I know the negatives are gone. And I have a tan theta cos 30. Cos 30, you can go ahead and use the OHA rule, or you can just use the calculator. For 30 degrees, it doesn't matter. Even if you use the special triangles or the OHA rule or even the calculator for 30 degrees, it will still give you the same answer. So cos of 30 degrees is root 3 over 2. That's fine. So we're just going to have tan of theta multiplied by the square root of 3 over 2 multiplied by sine of theta. And remember that already cancelled. So from here, I'm already going to change tan theta into its trig identity, which is sine theta over cos theta. Tan theta is equal to sine theta over cos theta. And then we still have that sine theta over there. And then this is being divided by sine squared of theta. Can already see how this is going to work out. We can see the sine theta, because these are fractions, as sine theta over 1. And let's multiply through. Here we're going to have sine times sine, which gives you sine squared theta, and we have root 3. So root 3 sine squared of theta over, and on the denominator here, not this, okay? On here, we have cos theta times 2 times 1, which gives us 2 cos of theta. Then divided by sine squared of theta, which I can say divided by sine squared of theta. Okay, so this is just going to be, even if you divide like that, it's going to actually work out fine. You can tip and times. Okay, for the sake of understanding, I'll tip and times. So this is over 1. We change the division into a multiplication and we tip that. So swap the numerator and denominator. So 1 over sine squared of theta. Okay, so now that we have that, you see that across, you must always check across if you have common factors. Sine squared of theta will cancel with sine squared of theta. That leaves you with the square root of 3 times 1, which is the square root of 3, over 2 cos of theta times the remainder of 1 there. So that's 2 cos theta. And that will be our answer. Okay, this is not root 3 over 2 cos theta. No, this is on the denominator. This one would be on the numerator. So that will be our answer. Okay, so that is our answer for 6.2. And then we move on to the next question. Okay, so 6.3 says, show that cos of 0 plus cos 1 plus cos 2, and keeps going to cos 178 all the way to cos 180 plus 6 sine of 90 degrees is equal to 6. Okay, so first of all, you see that the side that we are actually working on is the left-hand side. So I'll just start off by saying that I'm working with the left-hand side and rewrite it. Okay, and so this is all that we have here. Now, let's look at what can be simplified and what actually cannot be simplified right now. We can simplify that cos 0 degrees. That's a special angle. We can also simplify cos 180 degrees and 6 sine 90 degrees. So it's all of these numbers in between. That's the one that we actually have to do a little bit more in order to simplify. So I'm going to focus on these ones. Not that I'm leaving these ones out. I'll remember them. I'll bring them back into the sum. But I'm going to focus on these ones for now. So let me write these ones out. Okay, so this is what we have, right? Cos 1 all the way to cos 179 degrees. Okay, so let's think about how we can rewrite cos of 1. I see how cos of 1 can end up looking like 179 degrees. Do you notice these numbers? If you add them up together, like 1 degrees and 179, they give you 180. If you add 2 degrees and 178, they also give you 180. Okay, so what we can do here is, let us rewrite cos of 1 degrees in a way that we can actually work with, where it can actually cancel out with the numbers over here. So I'm going to rewrite cos of 1 degrees as cos 180 degrees minus what gives you 1? That's minus 179 degrees. Okay, so I'm changing the way it looks, not the value. Then this is plus cos of what is 2 degrees? That's going to be 180 degrees minus 178 degrees. Okay, and there you see 178 degrees. And we'll keep going. But in this pattern, when I keep counting, I notice that when I get to cos of 90, right, there isn't any number that can help to complete 90 other than 90 itself. But you see that we're counting as 1, 2, 3, 4, 5, 6, all the way to 90. Then we would have had 91 and 92 and so on. So in this one, right, before 90, you would have had cos of 89 degrees. And after 90, you'd have had cos of 91 degrees. Do you notice that the 89 and the 91, they would actually cancel with each other? And this is what I mean here. So as I'm counting, I counted the cos of 1 degrees and I changed it into this. The cos of 2 degrees, I changed it into this. If I kept on counting and I got to the cos of 89 degrees, right? Cos of 89 degrees, I would have to say cos 180 degrees minus what gives me 89 degrees. And that would have been minus 91 degrees. Then I would have kept counting and I would have gotten to that cos of 90 degrees plus cos 90 degrees, right? And then if I kept going, the cos of 91 degrees, I would just rewrite that as it is, right? I would have plus cos 91 degrees. And then this would continue 92, 93, all the way to cos 178 degrees. So now I have plus cos 178 degrees. And let me just actually write it as a number. And then again, plus cos 179 degrees. Okay, so I'm just trying to do this so that you can see what will cancel with what. If you simplify here, you see that this is cos 180 minus 179. On the cos diagram, 180 minus theta is in sine's quadrant. So it means cos is negative in this quadrant. So this would simplify to negative cos of 179 degrees, which is perfect. It will cancel with that positive cos of 179 degrees. Then would have, I can't really say plus yet because cos 180 minus 178 would give you negative cos 178, which would of course cancel with that positive cos 178. And all these other numbers will keep cancelling and then would have this one as well. That becomes negative cos of 91 degrees, which will cancel with this positive cos of 91. Then we have in that middle, kind of our middle, we have the cos of 90 degrees, not directly in the middle, but it's there. And then after having that 90 degrees, we're going to have now, I'm going to rewrite these as positive numbers as they are. So we have that cos 91 degrees plus cos 178 degrees plus cos 179 degrees. I'm just trying to show you how they actually cancel. Now that this happens, you see negative cos of 179 would cancel with the positive cos of 179 because they're being added all through. The negative cos of 178 will cancel with the positive cos of 178. Then as we keep going, all those other ones will also cancel with all the other ones on that side. And I should have still put 3 dots here, plus dot, 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 and then plus. Then the negative cos of 91 will cancel with the positive cos of 91, right? And you see that the cos of 90 is the one that didn't cancel. So all of that would be equal to cos of 90 degrees. Okay, now I'm going to put back the equation, the sum that we had. We were speaking about that left-hand side, right? You see that all of that, you can actually show them that all of that became cos of 90 degrees. So we still have here in green the cos of 0 degrees plus the cos of 90 degrees. And if we keep going, because that's all of that is done now, that's what's left. Then we have cos plus cos 180 degrees. And these are stuff that we can calculate, plus 6 sine 90 degrees. Okay, so this is actually what it simplifies to. And this is equal to Cos of 0 degrees, if you check on your calculator, the cos graph, cos 0 is 1. Cos of 90 degrees, however, is 0. Cos of 180 degrees, that is -1. You're just thinking about how the cos graph looks, it does that. Okay, and it's in intervals of 90. So that's 0, that's 90, that's 180, 270, and 360. Okay, you can use your calculator, but I'm just using the graph to remember what it's going to be. Cos 180 would give me -1, so -1. And then I have this sum plus 6 sine of 90 degrees. Okay, so do you see here, all of these simplify. 1 cancels with 1 and 0 is nothing. So you're left with 6 sine of 90 degrees. Sine 90 is equal to 1. And so 6 times 1 is 6. And that's how that is actually equal to the right-hand side, which is 6. Okay, so it's a long one. I'm sure there could have been a simpler way, but that's just how I thought about it in my head. Okay, so that's how that can be simplified. And that is the end of question 6. Moving on to question 7. Okay, question 7.1, they ask us to prove the following identity. So clearly we're going to start with the left-hand side. So let me write the left-hand side. Okay, so this is what we have. Let's go ahead and see. It needs to be equal to sine of x minus cos of x. So since we have sine of x minus cos of x, how about we just leave that? We can't really do anything with it. But this part, I can do something here. This is a double angle. So I can change it to its double angle. Okay, so we have -2 sine x cos x over, and we have sine x minus cos x. Now I'm seeing something here. The minute I see this kind of thing where I have sine x cos x, right, and I'm seeing a 1, I immediately start thinking of trinomials. This is the reason why I'm thinking of a trinomial. It's probably a trinomial that has sine x and a cos x in one of the brackets, right? So it could be like sine x plus cos x and then sine x plus cos x. That's how you got the 2 sine x cos x. So how is that going to actually work out? Well, we could change the 1. The 1, we could change it into its trig identity. Remember that sine squared of x plus cos squared of x is equal to 1. So I'm going to change that. So that's sine squared x and then plus cos squared of x, but I'll keep that one at the end. So I'll rewrite this -2 sine x cos x and then write the plus cos squared x over, and then I have this sine x minus cos x. So if you factorize this, right, it's like x squared minus 2xy plus y squared. If you factorize that, you know that it's going to become, because you're going to say what times what gives you x, that's x multiplied by x. What times what gives you y squared, that's y multiplied by y. And you can see that only the middle is negative, so they're both going to be negative. Likewise, this is going to be sine of x minus cos of x multiplied by sine of x minus cos of x, which is over sine x minus cos x. And you can see that they will cancel now. Okay, so sine x minus cos x ends up just canceling, and you're left with just sine x minus cos x, which is equal to our right hand side. Okay, so that's how we solve that one. Moving on to the next question. Okay, so 7.2, we have determine the general solution of this expression. So you see we have tan of 3x multiplied by this. Just because it has a tan, don't get intimidated by it. It's just a number. Just like sine 30 degrees is a number. It's a half. It's the same way 1 over tan 24 is also a number. So what we can do is, because they're being multiplied, they're one term, why don't you just take the -1 over? So we're going to have tan of 3x being equal to, and not being equal to, multiplied by 1 over tan 24 degrees, then is equal to +1. Now I need to get rid of this number, okay, because I want tan of 3x. This is just tan 24, it's just a number. So we'll divide both sides by 1 over tan of 24. So divided by 1 over tan 24 degrees. Okay, let's see what we get here. So this is going to be, we have tan of 3x, and those cancel, is equal to, you see you can tip in times here. This is 1, and we can change this to a multiply and tip this. So this is now tan 24 degrees over 1, which is just tan 24. So it means that tan 3x is equal to 1 times tan 24, which is tan 24 degrees. Okay, so this is what we have to find, the general solution of this. To find the reference angle first. Reference angle. It's kind of like solving for 3x, but not really 3x yet. Okay, just the reference angle. You would take tan over. When you take tan over, it becomes the second function of tan. Shift tan of this number, which is tan 24 degrees. Now let's see what happens when we do that. You see, if you say shift tan of 24 degrees, you get 24, because what happens is this is the second function of tan. It's the inverse of tan, and this is the actual function of tan. So they end up just canceling each other and simplifying. So our reference angle is 24 degrees. Okay, so then you can do that whole table thing. But let me already mention, in the case of tan, where you have tan being positive, you see we have tan of 3x being equal to tan 24. Tan 24 is a positive number. When tan is positive, you don't have to start thinking about all these quadrants. In fact, you can just go and solve for tan. I know most people will be like, okay, tan is positive in the first and the third quadrant. I mean, you can do that, but in general solution, you're still going to get the exact same answers because of the way the tan graph behaves. But this will not work for sine and cos. For sine and cos, I would say stick to this. But when tan is positive, you can just do this. We're just going to finally solve for 3x. And we'll say that 3x is finally equal to, and we're taking the reduction of the first quadrant. That's all. Beta. So whatever our reference angle is, which is 24 degrees right now. So I'm saying it's just 24. Then I must say how many times this is going to repeat. So I'll say plus 180 degrees k, or you could say k of 180 degrees. I usually like saying k times 180 so I don't forget the k. But even if you leave it like this, it's fine. Then I'll also tell them where k is an element of integers. And then now just solve for x. You don't have to say, oh, 3x is equal to 180 minus, I mean, you can if you want to, but in the case of tan, where tan is positive, it's not necessary. When you look for those specific solutions, you'll get the exact same answers all the time because of the way the tan graph behaves. Okay, I'll probably explain that more in another different video. Okay, so this is what we have. So we can go ahead and divide both sides by 3. And then if you divide both sides by 3, x is equal to 24 divided by 3 is 8 degrees. 180 cut into 3 parts is 60 degrees, so plus 60 degrees. And where k, of course, is an element of integers. So that's our answer there. And we move on to the next question. Okay, 7.3 says, determine the maximum value of this root 3 sine x plus cos x without the use of a calculator. Okay, this one actually looks familiar. I think I've seen something like this before. Now, if they just said determine the maximum value of sine x, or even just root 3 sine x, then the maximum value. So first of all, I just want you to understand the idea of what exactly a maximum value is. If the question was just find the maximum value of root 3 sine of x, because we have root 3 as the coefficient of sine x, it would mean that this sine graph, the highest it would reach is the square root of 3. The lowest it would reach is the negative square root of 3, right? So our sine graph would just look like that. And so its maximum value would just be the square root of 3. But the thing is, that's not what they said. They said square root of 3 sine of x plus cos of x. Now you cannot just say, oh, but the maximum here is square root of 3 and the maximum here is 1. So let me just add them together. No, they are one expression. You have to actually just simplify to a single trig ratio, then find the maximum value of that trig ratio. So how can we simplify this? So it is one of the ones that they don't actually bring up a lot, but it's actually one that you would need special angles for. When you see numbers like root 3, where do you remember seeing these numbers? I remember them from special triangles, or I'll call them, I use the OHA rule. So I remember them from the OHA rule. I remember having, for example, cos of 30 degrees being equal to root 3 over 2. Okay, so let me actually just write down that OHA rule so that we can see how root 3 can actually be written, the different ways it can be written. Okay, so this is the OHA rule. Let's see all the ratios that have the square root of 3 in them. So if you said square root of 3 being the adjacent, you can say adjacent over hypotenuse. So adjacent over hypotenuse, square root of 3 over 2. And remember, adjacent over hypotenuse is speaking about cos. The cos of what angle? Cos of 30 degrees, because that's the row that we're in. I just took the adjacent over the hypotenuse. That's cos of 30 degrees. Okay, I can try and work with this, cos 30 degrees. But you see, the issue here is that this says square root of 3, not square root of 3 over 2. So how do I get it to say square root of 3 over 2? What I could do is multiply this, right? That root 3 sine of x. I could multiply it by 1 in the form of 2 over 2. Because now that 2 is going to go to that denominator. Okay. Then the cos of x. The only number I actually see here, other than the cos of x, that variable, is an invisible 1. Right? So now, what should I change that to? Okay, I can change it to, I still have that positive 1 there. And of course, I have the cos of x. I can change this to 1 over 2, which is one of the three ratios we have. 1 over 2, and I can make sure that I keep it within the row of 30 degrees. So I'm looking in 30 degrees column, and I'm seeing what is 1 over 2. It's the opposite over the hypotenuse. So 1 over 2 is opposite over hypotenuse, which is sine. Okay, so that means sine of 30 degrees is actually equal to 1 over 2. So I'm going to try and change that to 1 over 2. And to do that, I would also do the same thing I did here. I'll multiply by 1 in the form of 2 over 2. Okay, so this is what we have here now. Now this is equal to, and I'm going to say I have the square root of 3 and I have this, but I just want to make the square root of 3 have a denominator of 2. So I can do this where its denominator is 1, and I'm saying the square root of 3, right? I still have that. And I'm saying 1 times the 2. So you see this 2 is gone because it's here now. It's under the root 3. Then we have sine of x times 2, which I can just leave as 2 sine x. Likewise with this, I'm also trying to form a half. So it's like the 1 times the 2, but I'm not going to times it by the 2. I'm just going to really take the 2 and put it over that 1. So it's like 1 over the 2. The 2 is gone. And then cos of x times 2 is 2 cos of x. Okay, so this is what we have. And we knew that root 3 over 2 is equal to cos 30 degrees. So I'm going to change that to cos 30 degrees. Multiply by 2 sine of x. And then we have plus 1 over 2, which is sine of 30 degrees. Make sure those angles are really the same. Okay, so then we have times 2 cos of x. See, I have not changed the value of it. I just changed the way it looks. That's the whole thing about maths at the end of the day. When you're problem solving, you're not changing the answer. You're just changing the way it looks so that you can better simplify it. Now look at this. What does this remind you of? It looks like the compound angle formula. It's just not in the right order. Okay, it's supposed to be in this order. So I'm going to change it. I'm going to change it to say, when I multiply these two, the sine should come first. I'm just going to say 2 sine x cos x. Cos 30 degrees, I mean. So that's sine cos, and then plus, we must have cos sine. So I still have the 2, so I'll say 2 cos x sine 30 degrees. And now it's in the right order. Sine, cos, cos, sine. Now, do you see that in this expression, there's two terms? And what's common in the two terms? We have 2 as a common factor. We can take it out as a common factor. So that means we have 2, open bracket, sine of x, and then cos 30 degrees, plus cos of x, sine 30 degrees. And this is equal to, and we still have 2, And now we can simplify that using the compound angle formula. So that will simplify to sine of x, and we're going to have x plus 30 degrees. Okay, so this is what we have. It's really just 2 sine x plus 30 degrees, which is perfect. We can actually find the maximum value of this. That's what we're going to do here. As you can see, this is a sine graph. It has been shifted 30 degrees to the left because it's saying plus 30. Plus, when it has to do with x, is left. Minus is right. But do you see now that the coefficient of sine is 2? So it means that if you had your sine graph, the highest it will reach is 2 and the lowest it will reach is negative 2. So do you see now that the maximum value of this graph, the maximum value is 2? And that's our answer. Okay, so that one is one of those ones that, yeah, it is a little tricky because this is not something that usually shows up. Okay, so that's 7.3. And we finally move on to 7.4, which is our last two questions. Okay, 7.4 says 7.4.1, they meant 4. Okay, sketch the graph of f for the domain where x is an element of negative 90 to 270 on the axis provided. Let me just go get the axes. So these are the axes they provided, and we're going to have to think about it like this. How do we actually draw this graph? Simplify it first. If you had 2 cos of x, this would just be the normal cos graph, but the only difference is its highest or the maximum value will be 2 and the minimum value will be negative 2. But now this is saying cos of x minus 30 degrees. Remember what I said previously? When you have x minus a number, that is actually the graph shifting to the right. So think about what the normal cos graph looks like, and every time you're going to shift to the right. So if I draw a normal cos graph that just went like this, right? What I would do is I would think of what the normal cos graph looks like. I don't even have to use that. I'll just think about what the normal cos graph looks like. And the cos graph usually does this at 0 degrees. But I just remember this is 2 cos, all right? At 0 degrees, the answer is usually 1, but because this is a 2 here now, the highest it will go is still 2. So I'll be like, okay, it's going to go there. Then at 90 degrees, it's going to be at 0. At 180 degrees, it's going to be at negative 2. And then at 270 degrees, it will be at 0. And then, of course, 360, it will finally be at 1 again. And then 90 degrees before this, it's going to continue with its pattern. You see that it keeps going 2, 0, negative 2, 0. Then it will go 2, 0, negative 2, 0. So here it would be at 0, okay? 90 degrees before this, which is at negative 90. Then if I can get this shape of the graph, right? If I can get it to look like that, then I will know that this graph is just going to look exactly like this. But because our graph was shifted 30 degrees to the right, my graph is just going to move 30 degrees to the right. So here, this is 90 degrees, 30 degrees later is at 120. So the graph would look something like that. Okay, then I would of course just continue that part. That part would just go down. So from here, it will touch here. It should touch here. Okay, then it will just go down. So I wouldn't really need these parts because it ends at 270 degrees like that. So like this, you can just remember whatever was the original value, the original y value at negative 90 degrees, that y value is now going to appear 30 degrees to the right, which now happens at negative 60 degrees. And whatever was your original y value for something like 0 degrees, that answer is going to appear at 30 degrees. Okay. So here at 30 degrees, we have 2, and at 120 degrees, you see that we have 0. And before we used to have at 180 degrees, negative 2, but that's now going to appear at 210 degrees. Okay, so that's really how you could do that. But you could also just punch it in one by one. That would also still work out, but it will just take longer. Okay, and then just to be more precise, I'll just write down those key points because I know that that's what they're really looking for. 30 degrees and 2. And I know they're looking for that. That's 210 degrees and negative 2. And of course, the x-intercepts, those would be important things. The y-intercept is not really very clear because it's not going to be a particular, it may be something that has decimals. And then this one is 120 degrees. So that's going to be 120 degrees and 0 as the y value. And then this would be negative 60 degrees and 0. Okay, so it's just thinking about what the original one looks like. And so what does this one look like depending on how it was shifted? Okay, so that is 7.4.1. Moving on to 7.4.2, which is the last question for this paper. Okay, so 7.3.2, they say use the letters P and Q to indicate on the graph the solution of the equation, and this is the equation they give us. Cos of x minus 30 degrees is equal to 0.5. Okay, and x coordinates of P and Q, and the x coordinates of P and Q. So we just need to tell them the actual x coordinates of P and Q and indicate where they're going to be, okay, on the graph. So in order to do that, look at the equation they've given you. It looks very similar. It looks exactly like the other one, just there's something different. Do you see that the equation they gave us here is 2 cos? So do you see that the 2 is missing, right? So to know where it is, we can of course solve for this, but to know where this is going to be on the graph, I would actually try to turn this into this. I try to make it look like that. So I need that 2 to be back there. So I will multiply both sides by 2, just so that I can see where exactly is it. Where's the solution happening? So that's 2 cos of x minus 30 degrees, and that's equal to 0.5 times 2. That's a half times 2, and that's 1. So this solution that they're speaking about is happening where the y value is 1, which is here. So the y value is 1 over here. So the solutions for P and Q is probably this one here, but because of my terrible drawing, it's not really showing well, and this one here. Okay, so now we actually have to write that down and actually find out what exactly those x values are, because they told us to also show them what those x values are. For that, I will just continue with the simplified form, because either ways I'm still going to divide both sides by 2. So I'll continue with this cos of x minus 30 degrees is equal to 0.5, or just say a half. Okay, so 1 over 2. And now how do I actually find the solutions? It's not necessarily general solution, because you can see where those solutions are happening. They're here and here, right? So look at this, and this is now a completely different direction to how general solution would work. It's slightly different. So if we were trying to find those, they're just those x values. You actually have to look at where it is. I know with general solution, where when cos is positive, you draw your quadrant, and that's why you need to know more than one method, honestly. But it's still okay. You can still think about it with this. When you draw your quadrants, you'll be like, cos is positive in the first and that quadrant, right? And this quadrant, the reduction is just theta, and here's 360 minus theta. If you use 360 minus theta, the x value you're going to be getting is the one that comes after. So you're going to get, this is your theta, whatever that is, and then that 360 minus theta is the x value that comes here. Okay, and as you can see, 2 cos of theta, right, for these intervals is only ever equal to 1 here and here. Okay, the graph does not continue enough for you to see the next place where this graph is going to have a y value of 1 again. So this is why in this case I wouldn't really use this. I would just try to understand how the cos graph works. The cos graph, how we're going to find these values would be like this. Let's look at the cos graph and just understand something about it. It is a graph that is symmetrical, right? If you had a normal cos graph, just this one that looks like that, and let's just say you had another one here, right? And we're trying to find out where cos was equal to, let's just say a half, right? So let's just say a half here. In order for you to find this and this, because it's that solution that is between that y-axis, okay? So this is where cos of x, for example, is equal to a half. You take cos over and become shift cos. So x is equal to shift cos of a half, which is 60 degrees. So look at how this is going to happen, right? That's really your reference angle. Where this will appear is going to be in these places. That first 60 degrees is going to appear here, right? That's 60 degrees. And this one over here is going to be the negative of whatever this is. So that's negative 60. Okay. Similarly, we're going to have to look at this one like that. So yes, we can go ahead and take cos over, right? And let's just say, for this case, I'm not really going to say reference angle because I'm not trying to find the general solution. So x minus 30 degrees is equal to, and I find shift cos of a half, which I know is 60 degrees now. What I'm saying is, if this was my reference angle, which is really what I was actually supposed to call it, but I didn't want to because I'm just trying to solve for x. If this was my reference angle, I showed you now that on the original cos graph, right, when we're trying to find out where the y value is a half on the cos graph, it happens at positive 60 and negative 60, just because of the way the cos graph works. It's symmetrical. Okay, so that's what's going to happen here. This 60 degrees, what I'm going to see this as is a positive and a negative 60. So for the sake of understanding, I will just say reference angle, but then it's 60 degrees. But when I'm actually solving for x, I'll say therefore, it either means that x minus 30 degrees is equal to positive 60 degrees, or x minus 30 degrees is equal to negative 60 degrees. And that will get those two solutions on the side with the cos graph. And so x is equal to, we take the negative 30 over, and that becomes a 90 degrees when added to the 60. And if you take the x, that over negative 30 over, that becomes a positive 30. So negative 60 plus 30 is negative 30 degrees. You see your x values are x is equal to 90 and x is equal to negative 30 degrees. So there, that is that and that. Okay, and then on the graph, that's what they are. They said indicate them as P and Q. So that's going to be our P, and that's going to be our Q. Okay, so that is the last question for this paper. That is the end of this paper. Okay, so grade 12, just remember, this is just a series of videos that I'm making as a prep for March 2024's papers. Hope you guys enjoyed this paper. It had some troubling parts. If you've enjoyed this video, please make sure to leave a like and subscribe for more content. And I will see you guys in the later videos. Bye for now.